Today's lessons are further studies of angles. Let's talk about central angles. In a circle, a central angle is an angle whose vertex is the center of a circle and whose radii are rays of the angle. The central angle is often denoted by the Greek letter theta. And so we have R1, R2, and between them we have the angle theta. There are 360 degrees in a full circle, so the diameter of the circle is a central angle whose measure is 180 degrees. A quarter of a circle corresponds to a central angle of 90 degrees. It's easy to convert between the central angle and the corresponding arc length. In the diagram to the left, the length of the arc connecting points A to B can be found by considering the ratios. Theta over 360 degrees is equal to this arc length AB divided by the full circumference. Of course, the full circumference is 2 pi r, so the ratio theta to 360 is equal to the arc length divided by 2 pi r. So, for example, if this arc length AB were 3 pi and the radius of the circle were 6, to find the central angle, we'd say 360 degrees times 3 pi over 12 pi, which is of course a quarter, so 90 degrees. The ubiquitous clock face problems. So in a clock with 12 digits, the central angle corresponding to 1 hour equals 360 degrees divided by 12, which is 30 degrees. So at 3 o'clock, for example, the hands of a clock form a central angle of 90 degrees, right? We'd have one hand pointing up at the 12 and the other pointing up at the 3, forming a right angle. So when you're dealing with these clock face problems, you should assume that the hour hand moves continuously as the minute hand moves. So at 3:30, the minute hand is pointing down at the 6, and the hour hand is midway between the 3 and the 4. For example, what is the angle formed by the hour and minute hands when the clock reads 3:30? Well, each hour of separation between the hands is 30 degrees. So at 3:30, we have 1 hour, 2 hour, a half hour, so 75 degrees. Clock face problems are often given to the nearest minute, and you have to learn how to compute the angles on a minute by minute basis. So let's think about, in 1 minute, the minute hand moves 1/60th of the way around the circle, which is 1/60th of 360 degrees, or 6 degrees. The hour hand moves 1/60th of 1/12th of the way around the circle in 1 minute, so that's half a degree. Computing the position of the minute hand at a given time is straightforward. The angle formed by the minute hand and the line pointing straight up to 12 is 6 degrees times the number of minutes past the hour. The angle formed by the hour hand and its position at the top of the hour, that is, at 0 minutes past the hour, is 30 degrees times the fraction of the hour that has passed, which is a half degree for every minute past the hour. So if you want to calculate the angle formed by the hour and the minute hands when the clock reads 3:42, we're first going to find the angle between 12 and the minute hand at 42 minutes past the hour. Then we're going to figure out the angle between going straight up to 12 and the hour hand at 3:42. And then we're going to subtract this angle relative to 12 to this angle relative to 12. And their difference is the angle formed by the clock hands. So the minute hand is at 42/60 times 360 degrees with respect to 12 o'clock, which is 252 degrees. The hour hand is at 90 degrees when it's at 3 o'clock, and then we figure out it moves 42/60 times 30 degrees with respect to vertical. So this is at 111 degrees with respect to 12 o'clock, and therefore the angle formed between them is 252 minus 111, or 141 degrees. So the inscribed angle theorem tells us how to calculate inscribed angles if we know the central angle, and vice versa, and is extremely useful in these math contests. So let's first describe what an inscribed angle is. An angle is said to be inscribed in a circle if the vertex of the angle lies on the circumference of the circle and both rays extending from that vertex intersect the circle. So it could be like case A, where the vertex is here and one ray goes through the center and hits the circumference here, and another ray hits the circumference there. So that's inscribed angle psi. Inscribed angle psi could also happen if a vertex is here and the two rays go to either side of the center before they hit the outer edge of the circle. And in case C, the vertex is here and both rays lie on the same side of the center as they intersect the circle. But regardless of which case we are, we'll be able to prove that for any given arc on a circle, the measure of the central angle of that arc is twice the measure of any inscribed angle to that same arc, no matter where the vertex of that inscribed angle is. So again, because this theorem tells us that this relationship between angle theta, the central angle, and angle psi, the inscribed angle, is the same regardless of where the vertex is, you have to be able to show it's true for these three cases, because these are the three possible relationships between the vertex location and the two rays. So the first case we're going to prove is case A. So that's where the two rays are such that one ray passes through the center and actually forms the diameter of the circle, and the other ray moves to one side. So we're going to only prove case A here in the notes because cases B and C are left as exercises. So let's look at the proof of case A. So in this diagram, we have OA and OB. They're both radii. So triangle AOB is isosceles. And so since it's an isosceles triangle, this angle is psi, and this angle must be congruent to that and is also psi. Since the sum of the angles in that triangle has to be 180 degrees, angle AOB plus 2 psi is equal to 180. But angle AOB and the central angle theta form a line, so they have to be supplementary. So AOB plus theta is also equal to 180 degrees. So subtracting these two relations, we show that theta has to be equal to 2 psi, which was what we were trying to prove. There's an important corollary. Any two angles inscribed to the same arc on a circle must be congruent. And the reason is their measures are both equal to half the central angle to that arc. If their angles are equal, then they're congruent. Okay, let's consider an example of a right triangle inscribed in a circle. Triangle ABC is inscribed inside a circle centered at point O with radius 6.5. Side AC passes through point O. If AB is 5, what is the length of side BC? Okay, side AC is a diameter because it passes through point O, the center. So, arc AC is half of the perimeter, so central angle AOC is 180 degrees. By the inscribed angle theorem, angle ABC is 90 degrees, right? Because AOC is 180 degrees, inscribed angle to the same 2 points, A and C, so inscribed angle ABC is half of central angle AOC. So by the inscribed angle theorem, angle B here is 90 degrees. So this is a right triangle. Well, one side is 5, the other side is a radius plus a radius, the other side is 13. That's the hypotenuse. So you recognize the Pythagorean triple 5, 12, 13, and BC is 12. So this problem illustrates the important point that any triangle inscribed in a circle with a side passing through the center of that circle must be a right triangle, and the side that passes through the center is the hypotenuse of that right triangle. In a triangle, a median from a vertex to the opposite side bisects or evenly divides that side. So it's easy to prove that the median to the hypotenuse of a right triangle is equal to half the length of the hypotenuse. Okay, so we're saying for any right triangle, if I draw the median connecting from the angle, from the right angle to the hypotenuse, this length of this median is going to be equal to half of the hypotenuse. And as you could tell by the figure I've already drawn, we're going to use the inscribed angle theorem to show this. So in the illustration here, we take advantage of the fact that any right triangle can be inscribed into a circle where the diameter is the hypotenuse. That median is also a radius of the circle, right? If we've inscribed this, OB is a radius. But wait a second. O is the center, so OA is a radius, and OC is also a radius. So the median, OB, is equal to half the length of the hypotenuse, AC. And this is true for any right triangle. So now let's talk about the power of a point theorem. This theorem is very useful in math contests, but usually shows up more in high school level contests. At the middle school level, the Alpha Star Fermat and the Purple Comet contest often have questions based on this theorem. So there are 3 cases to consider, case 1, case 2, and case 3, but in each case, given a point P and a circle, pass 2 lines through P that intersect the circle in points A and D and B and C respectively. Then distance AP times distance DP is equal to distance BP times distance CP. So when we're dealing with case 1, this is called the intersecting chord theorem because AD is a chord of a circle and BC is a chord of a circle. They intersect at point P, and then we basically know that BP times CP is equal to AP times DP. So let's prove case 1. And again, cases 2 and 3 are useful to remember and know how to do because the intersection, this point P, can occur outside the circle. But let's start by proving case 1, and the other proofs will be left as exercises. So angle ABC and angle BCD are equal to one another because they're both inscribed into the same arc AC. Angle BAP and angle DCP are equal to one another because they are both inscribed into arc BD. And angle APB is equal to angle CPD because they're vertical angles. So these triangles are similar by angle-angle or by angle-angle-angle. And so because of the ratio of the sides of similar triangles being the same for all respective sides, we know that the ratio of AP to CP is equal to the ratio of BP to PD. So cross multiplying, we have the relation AP times DP is equal to BP times CP. So let's use an example of the intersecting chord theorem. So DEB is a chord of a circle such that BE equals 5 and ED is equal to 3. EC is equal to 1. Find the radius, so O is the center of the circle. Find the radius OC of the circle. So you might think, well, I want to use the intersecting chord theorem, but I don't have two chords. Well, you don't have two chords yet. Let's extend OC all the way out to this edge of the circle, forming a diameter, which is, of course, a chord. So this distance, O to here, is the radius. OC is the radius. So using case 1, we have BE times ED, 3 times 5, equals EC, 1, times the distance from E to this edge. Well, that's 2 times, that's EO plus the radius, okay? So EO plus the radius has to equal 15, but we know EO plus 1 is the radius, so EO equals 7 and the radius is 8. So you see, we could use the intersecting chord theorem because this point was going through the center, so therefore we knew the relationship between this side on point O had to be the same as radius OC. So let's look at the exercises. What is the angle less than 180 degrees formed by the hands of a clock when the time is 10:16? 2, at noon, the minute and hour hands are both pointing directly up to 12. If the hour hand moves continuously, at what time will the minute and hour hands next form a 181.5 degree angle? Exercise 3. A triangle inscribed inside of a circle divides the circle into 3 arcs whose lengths are in a 3:4:5 ratio. What is the measure of the largest angle of the triangle in degrees? 4. At some military bases, and actually in most countries of the world, time is measured on clocks with 24 hours on the face of the clock rather than 12 hours. So 10 p.m. is 22. What angle less than 180 degrees is formed by the hour and minute hands at 22:30 hours, half past 22? 5. In the figure here, if the length of the radius BP is 15, what is the arc length AB in terms of pi if angle A is 38 degrees? 6. In this figure, quadrilateral ABCD is inscribed in circle P with radius 5. What is the arc length BCD in terms of pi? So when we give a point in an arc length, that defines which direction we're going around the circle. So we want the arc length that goes from B through C all the way to D in terms of pi. 7. Point A is drawn outside circle O so that AP is tangent to the circle. We extend chord CB outside to point A so that CB is equal to AB and AP is equal to 3 times the square root of 2. What is the length of AC? And exercise 8. Diameter AB of a circle has length 25. Point C is chosen along the circumference such that AC has length 7. What is the length of BC? Okay, in the figure at the right, the small circle has its center at P, while the big circle has its center at C. If PA equals 3, and BC equals 4, and PC equals 6, what is the length of AB? The figure is not exactly drawn to scale. 2. Angle CBD and angle BCA are inscribed in circle P, whose radius is 5. The arc lengths BA is pi, and CD is 3 pi. What is the measure of AED in degrees? So what is the measure of angle AED in degrees? 3, as promised earlier in this lecture, prove the inscribed angle theorem for case B as shown in slide number 5. As a good hint, use the proven result for case A as the starting point in your proof. In other words, you don't have to reprove case A. You can use the result of case A to prove case B. And 4, prove the power of the point theorem for case 2 as shown on slide number 7. Okay, that's it for this week. See you again next week.